Hey, good morning, everyone. I'm gonna go over some problems Chris had asked, and so um, and I think this can help you to guide your thoughts for the upcoming exam. So in chapter three, this is good. So you should review and be able to do those things. This is good too. This is good. Review that. Multi-slits interference. This is sloppily done in this book. Um, I can't follow the demonstration they do. Young and Friedman, the book we were using before, they do a better job. So, but don't worry. Make sure you know Young interference with two slits and and um, and that's it. The diffraction pattern of two slits. Interference with thin films is okay. I mean, this is good, and I know that a couple of you are doing projects on it, so this is good. Um uh, and 3.5, read it, but don't worry about it. I guess that's it. So you have the key equations are pretty much similar to those that will appear in the next chapter, chapter 4. Okay, so let's take a look at some of the problems. Number 16. Pull my paper. So, oh, wait a minute. At what angle? So, number 16. At what angle is the first order maximum? So, double slit. Separated. So, the distance is given d, right? D is 0. I'm doing this assuming you have no idea how to do that, but I think by now you guys are comfortable with this. But anyways, uh, so you have an interference pattern that goes something like this. So go there, that's order 0. Then you have another one and another one, and then you go like that. So um, basically d sine theta is equal n lambda. N has to be an integer number of um, n has to be an integer number so that d sine theta, which is equal to the change in light rays, light rays that goes from here, let's say, to there. So R2, R1. So the difference in pathways is equivalent to an integer number of wavelengths to ensure you have a bright region in there. Okay, so we want to find the angle. So sine theta is equal. We want a first order, so m equal 1 is lambda over d, and then we plug the information given right, 450 nanometers. So just get the units correct, divided by d, the separation 0.05. Oh no, it's millimeter, 10 to minus 3 meters, and then you can get your angle. Okay. So 17, 18, let's try 19. 19. Find the distance between two slits. Now we want to find d. So in 19, now we want to find d. We don't know. And the first minimum, so m equal 1. Oh, first minimum. Oh, wait a second. The lambda is equal to 410 nanometers. The angle is given. Angle is given, and so we are talking about first minimum. So we are kind of right here, right? We are right there. First minima. So to ensure that del R gives destructive interference, so we have a different equation. We want the separation between the two light rays, the path, the separation between the path of the two light rays to be equal to half numbers of wavelengths, basically. So we want to here m equals 0. M equals 0. So you want to del R. Why did I put lambda? Del R to be equal lambda over 2. Okay, but sine theta, in fact, this angle here is theta, and this is basically del R, assuming these two rays are parallels, which means you have to have the screen at a separation that is large. So these two light rays become parallel. You ensure this is a 9 degrees angle, and then your sine theta is going to be equal to del R divided by d, right? Del R divided by d. So then you plug sine of 45 is equal del R, which is lambda over 2, divided by d. And then your d is equal lambda, which is given 410 10 to minus 9 meters, divided by 2 times sine of 45. Then you can find your d. Okay. What else? How about 21? What is the wavelength? I never know which ones you have solutions. Is the odd or even? No, I don't know. No, let's try 20 instead. Calculate the wavelength of light that has its third minimum at an angle of 30 degrees when falling on double slits separated by some distance. 3 times 10 to minus 6 meters. Okay, so we want to find the wavelength, the third maximum. So again, del R, the separation, um, the difference between light path rays is given by this equation to have a minimum. And we wanted the third. Oh, that's the confusing part. Third minimum. Okay, third minimum. Third minimum. That goes like this. So this is the first minimum for m equals 0. Second, m equals 1. Third, n equals 2, right? So this is m equals 0. Because could be plus or minus. So this is m equals 0. M equals 1, right? And m equals 2. Then, so we want a third minimum, n equal 2, so del R is equal 5/2 of lambda on the 20. And the angle is 30 degrees, so sine of 30 is equal 5/2 of lambda divided by d. So then we can solve for lambda. Lambda is equal to d times sine 30. That divides 5. And these problems, they all seem to be the same, right? So they keep on repeating themselves. Let's see, 33. Uh, 33. If 500 nanometers, 650 nanometer light illuminates two slits, they are separated by that. How far apart are the second order maxima of these two wavelengths on the screen? Oh God. Okay, two slits, same idea. So let's take the lambda. That is what's going on for this lambda 500 nanometers. The separation is given. Separation is given. Second order maxima. I'm going to call this order 0. Order 1. Order 2. M equals 0, 1, 2. Second order maximum. So I'm taking this one. Order 0, order 1, or order 2. So I'm going to take m equal 2, so it's maximum. We are trying to find y2, right? Y2. So basically, sine of theta is del R over d, but it's also equal to ym divided by d. So the y2 of 500 nanometers is equal to big D m lambda divided by little d, which is d that separate times 2 times 500 nanometer divided by 0.5 10 to minus 3. And d is given, right? It's 2 meters away. So then you find a number here. Now the other 2 for the other wavelength, 650, is equal to the same thing, 2 times 2 times 650 nanometers divided by that. So what you want to do is to find out how these two numbers separate themselves from one another. Okay. So let's do the last one on this, number 34. So what's going on with 34? Oh, God, we have a red light. The wavelength is 700 nanometers. Falls on a double slit separated by D. This 400 nanometer. At what angle is the first order maximal in the diffraction pattern? Okay, so the same idea. At what angle is the first order maximum? So first order maximum means m equal 1. So we are talking about sine theta is equal m lambda divided by d. That would give lambda 700 nanometer divided by d, 400 nanometers. And then the angle can be determined. 7 divided by 4, right? Yeah. Something is weird. You can't have that. Sine has to be less than 1. What's going on here? That's what's going on. This is not that something is wrong with the argument here, because to have interference, the wavelength must be at the size or less than the separation between the slits. Otherwise, there is no interference, right? That's why there is no interference if you have white going through your window or two of your windows, because the wavelength separation is too big here. I mean, there is, but you can't see it. Yeah, what is the condition for interference? You have to have the wavelength that falls on the double slit must be comparable with the separation of the slits or less. So if that is not complied, then there is no interference. So I don't know what's going on. Something is wrong. And I think I remember some of you commenting on that. So, oh, what is unreasonable about this result? Okay, so this is unreasonable. Okay, so that's it. Let me go to, let me give a break. Then let's go to the other thing interference.